Hi, welcome to the course on artificial intelligence. As we have seen earlier, we understood what is the history of AI, and we also understand how do we define AI in four broad aspects. Now we are going to discuss about the intelligent agents, what they are and how we can build them. Let's get right ahead. The goal of AI is to build intelligent agents. In this, we are going to be talking about what should be the design principles for building such intelligent agents. A successful agent is something which we can reasonably call as intelligent. So what is an agent? Agent is something that takes input from environment through sensors, uses the input information to select an action, and acts upon the environment using actuators. So let us look at some of the examples. If we talk about a human agent, the input sensors are eyes, ears, and the inference usually happens in the brain. We process that information from our sensors, and then we act upon the environment using actuators like legs, hands, vocal tract. If you look at a robotic agent, the input sensors are camera, infrared range finders, and the inference, which is the processing of this information, happens through control theory, and we act upon the environment using motors as actuators. Whereas if you look at a software agent, the sensors are usually the keystrokes that we type in, the file contents, or the network packets. And we do the inference usually using an operating system. And then we actually output whatever the information that we have processed through display on screen, or writing back to files, or even sending network packets. So these are some of the typical examples of agents that we see in our everyday life. Let us look at some of the key terms that makes up an intelligent agent. Percept. Percept is nothing but the inputs that agent would receive from the environment. Like in the example of human agent, eyes, ears, and in the case of software agent, the keystrokes from a keyboard. These are some of the percepts that an agent would receive. A percept sequence is a sequence of percepts the agent would receive in a history of time. Whereas an agent function is a mathematical notation of defining what would an agent would do once it receives an input from the environment. So if you actually see a car coming your way, what would you do? You move out of the way. This action of moving out of the way is something defined as an agent function. This is represented mathematically. Whereas the agent program is nothing but the implementation of the agent function. We encode this mathematical construct, and we write a programmatical algorithm to implement this in a concrete form. So now that we understood what an intelligent agent is and what are its key terms, let us look at what a rational agent is, which is our main topic of building artificial intelligence agents. A rational agent is the one that does the right thing. But what does it mean to be right? So being right has its own definition, where it depends on four aspects together. One is a performance measure. Performance measure is something that we actually try to optimize for. Let's say you are trying to reach your destination. Let's say you are going to an airport. How soon can you actually reach your destination? That is your performance measure. Agent's prior knowledge of environment. So if you are actually going through a particular route, you already have a prior information that there might be traffic on a particular direction. So this is something that you already know about the environment. That's a prior knowledge. And what actions that the agent can perform. You can take multiple actions. In the case of driving a car, you can actually use your steering to take a left turn or right turn, or you can brake, or you can accelerate. These are all the actions that can be possible while you're building a self-driving agents. And finally, the percept sequence till date. What has been received by the agent so far would also form the part of being rational. So in order to define being rational, it is about selecting an action from a possible set of actions based on the information of percept sequence and the prior knowledge together, so that the selected action would optimize the performance measure. So at the end of the day, being rational is about selecting an action, and you select this action based on percept sequence as well as prior knowledge. These two combined would help you find that action among the possible set of actions. However, you can't actually select any action from the possible set of actions. You should be optimizing for the performance measure, and you select that action which would optimize that. So to summarize, the components of a rational agent would be: 1. Performance measure, which is denoted as P; environment's prior knowledge, which is denoted as E; actuators or otherwise actions, which is denoted as A; and with the percept sequence, which is nothing but the sensors, so S. In short, we can refer it as PEAS, P-E-A-S. These are the components of a rational agent. So all is well, we have understood them, but let us look at some of the examples in some of the agents that we usually interact with. If you are looking at a medical diagnosis system, a medical diagnosis system is one which takes input from patient symptoms and tries to give a diagnosis on what to do and what has happened to the patient based on the symptoms. So this is an automated, you can call it as a chatbot, which works on patient's data as well as hospital diagnostic information data. In that particular agent, our performance measure is to improve the patient health. At the same time, you want to reduce cost for the hospital. Whereas the environment, you can think of environment as all the objects that this agent would interact with. So in this scenario, it would interact with the patient, it would interact with hospital or the staff. And the sensors this agent would receive are the symptoms of the patient, all the findings that the doctor has reported, and any patient answers to the questions posted by the system. The actuators is nothing but the actions that the system can take are displaying questions to the patient, or asking for the test, or even giving a diagnosis on based on the symptoms, or even doing a treatment, or even giving referrals. So these are all the possible actions that this medical diagnosis system can take. So if you move on to the next example, which is satellite image analysis system, what this system does is it looks at an image sent by a satellite and categorizes that image into a certain set of categories. So the performance measure here is to make a correct categorization. Let's say you got images of a forest. Can you categorize them whether they belong to forest A or forest B? So in this case, the environment is the object that is interacting with is the downlink from the orbiting satellite. And the sensors that it would receive is the color pixel analysis. Each image would have a lot of pixels, and that would be the input that the system would receive. Coming to the actuators, it is simply the display of scene categorization. Whatever the output of the system is, that will be going to be displayed for this system. And another example is interactive English tutor, where this agent tries to improve a particular student's English ability by helping him guide in the right direction of asking the right questions or with giving the right knowledge of English language. So here the performance measure is to improve students' score on any test, and the environment it interacts is with a set of students as well as the agency which actually tests how these students are performing. The sensors are nothing but whatever the student types in, whatever the answers that student would give through keyboard, and the actuators are how this agent is going to interact with the students in the form of exercises, or it can give you suggestions or corrections. Like if you think of a simple example will be a Microsoft Word, where you're just typing in and there might be a grammatical mistakes or spelling mistakes, and the word Microsoft Word would give you a suggestion with a underline, with underscore. So these are some of the interactions this tutor would have with a student. Now that we understood what forms a rational agent, the components of a rational agent as performance, environment, sensors, and actuators, one key thing that is quite not so obvious is the environment aspect, where we are talking about environment as a set of objects like patient, hospital, staff, but we don't really understand what do you mean by a patient or a hospital. How does this agent interact with this environment? So let us try to understand the environment in more detail. A rational agent is built to solve a specific task. At the end of the day, we want a solution for a task. So we define the environment for the task as task environment. So in order to understand task environments, we need to understand what are the variants of a task environment. One such variant is fully observable versus partially observable. What does fully observable mean is if an agent sensors give it full information about the state of the environment. The state of the environment here is a key term here. You need to understand what a state is. So if you think a state is a snapshot of what is happening with the environment at any given moment of time. Let's say you are playing chess and let's say you are not making an action. If you take a snapshot of the chessboard, that constitutes as a state for that particular game. Similarly, if you're driving a car, if you take a snapshot of where your vehicles are, where is your traffic is, where is your signals are, that all constitute as a state of the environment. So if you actually have the complete information about the state, then that is a fully observable environment. Like in the example of chess, you have entire information of where your all your places are, where your next move is. But if you're looking at a partially observable environment, you don't have full information, wherein if you're looking at a driving vehicle, you don't have what speed your vehicle beside you is traveling at, how much of brake the front vehicle has applied, and when is your signal going to stop. So there is some variability in terms of the state of the environment. So in such scenarios, we call it as a partially observable environment. The other variant of task environment is a single agent versus multi-agent. A single agent is an agent solving a crossword puzzle all by itself. Like there is no other player involved in that game. That's a single agent. A chatbot is also a single agent. A multi-agent is where you have two agents working together in that environment. They might be playing against each other or they may be working together. So all those scenarios constitute multi-agent. The other variant is deterministic versus stochastic. Think of it as a function of a state and an action. So imagine you have a chessboard and you have performed an action of moving your chess piece from one place to another place. Every single time you do that, you are determined that this would result in the same exact state every single time you do the performance. But imagine you are playing a carom board and you actually do a strike in the same direction, but every time the end result would be different. The end resulting state would change every single time you attempt the same action at the same state. So that would be a stochastic environment. Like a carom board would be a stochastic environment. Stochastic is nothing but being random. Deterministic is making sure that it results in the same state every single time when an action is taken at that given state. The other variant is episodic versus sequential. Episodic is where the agent's current action doesn't impact the state of environment for the next action. Like if you're building a spam classifier and you got an email where you want to classify that into a spam or not spam, the performance of that classification doesn't impact what the next email is going to be. So that is episode by episode. The next episode will be different, the next email will be different, so it doesn't really depend what you have done in the previous action. Whereas sequential, the current action would determine what your future actions are going to be. Like if you are thinking of any board game, whatever step that you take now is going to determine what you're going to play next. So that is a sequential environment. Static versus dynamic is another type, where static is the environment can change while the agent is deliberating is called dynamic. So if you are thinking of a video game, like you're playing Mario and any other element is interacting with the environment while you're taking an action, that is a dynamic environment. The state is keep changing while you're deliberating on an action, while you're thinking of an action. Whereas a static is something that doesn't change even while you're thinking of taking the next action, like in chess. Discrete versus continuous. This is more about the state of the environment. As I was saying, what are the possible states of an environment can be classified into discrete versus continuous. Again, in the case of HS, there are only a finite number of possible states. There are only a finite number of possible combination of pieces that you can arrange on the chessboard. While if you are thinking of a self-driving in a self-driving car, there is a continuous state and continuous time problem. You can have a variation in the amount of pressure that you apply on the brake. You can steer your vehicle with minute differences. This would all impact where you're going to be in the next second or the next couple of seconds. This is a continuous space you are interacting with in a self-driving environment. Whereas in HS, it is more of a discrete environment where your states are finite in amount. So these are all the variants in a task environment. If you look back at whatever examples that we are looking at, that is the medical diagnosis system, the satellite image analysis, or interactive English tutor, we can define each of those tasks and what kind of environment they are dealing with. So if you look at medical diagnosis system, the first part is fully versus partially observable. You can think of this as a function of sensors, as in how your sensors are giving input to your environment. If there can be noisy sensors, there can be sensors which can't look at the entire environment. So that would determine are you having a fully versus partially observable. In the case of medical diagnosis system, the patient wouldn't actually able to tell all the symptoms, or he may not be able to give you the full context of what's happening with his body. So there you have a partially observable environment. Single versus multi-agent. Here in the medical diagnosis system, there is only one agent that is trying to identify the diagnosis of the patient. So it is a single environment, single agent environment. In deterministic versus stochastic, here what we are trying to do is what would be the function of state and action. Given what you know about the patient, if you diagnose the patient with a particular treatment, what would be the end result? This would determine on the patient's body type, patient's history. So it is more of a stochastic environment where we can't really be sure that this would be the end result of this particular treatment for this patient. So you can think of it as a function of what is the state and what kind of action, and where would that end up with. In episodic versus sequential, here each single decision depends on what you have taken earlier. Like if you want to take state at t+1, is it a function of state at time t? So that would be a sequential for a case of medical diagnosis, because you keep looking at the patient, you see the progress of the patient, and you keep changing your treatment. So it is a sequential environment. Static versus dynamic. Here the medical diagnosis system is a dynamic environment, because while you're deliberating, while you're thinking of the treatment, in the case of a patient in an ICU, there may be many variables that are changing. So while you're deliberating on action, there might be a situation that has worsened, or there might be improvements in the patient. So you can't really be sure that the situation has stayed the same. So it is a dynamic environment. Discrete versus continuous, again the state space, the number of variables that go into a treatment are many, that it is a continuous environment. In the satellite image analysis system, we have the sensors, that is nothing but the satellite sending you the image. So there is not much of noisy there, and so we consider that as a fully observable environment. Again, it is a single agent because there is only one satellite and there is only one analysis system that is working with that. Deterministic versus stochastic, as we see that the categorization is the same no matter what kind of image is given again and again. So it is a deterministic environment. Episodic versus sequential. So every time you get an image, you just repeat the action of categorization, which doesn't really determine what your image is going to be at time t+1. So it is an episodic environment. Static versus dynamic. Well, it is a static environment because there is not much of change in the environment, as you see. And discrete versus continuous, if you see like an image will be made of a lot of pixels. So each pixel would have range of values. So the state space in this particular system is continuous. So similarly, for English tutor, you can do this exercise and then verify your understanding of this environment. So now that we understood the environment and its variants, let us look at how do we build our rational agents. So building rational agents is all about designing agent programs that would implement the agent function. As I said, agent function is nothing but a mathematical construct that would map percepts to actions. Given a percept, a function would map that to actions. So this is constructed mathematically and we call that as agent function, and whenever we actually implement this, we call that as an agent program. So there are really 5 ways of designing such rational agents. They are listed here as simple reflex based agent, model based agents, goal based agents, utility based agents, and learning based agents. We're going to be discussing each one of those now. A simple reflex agent are the agents that selects actions based on the current percept alone. It only looks at what is the current information that it receives from its sensors and then selects an action. It ignores the rest of the percept history. So if you think a few of the examples are like, if the car in the front is braking, you just apply the braking without actually knowing what has been done in the previous past. Such rules are usually also called as condition action rules or simply if else, because they are pre-coded and you see them and you do the action without actually verifying with your history. So if you take an example here, let's say you have a vacuum cleaner and there are 2 possible rooms, room A and room B, and you have dirt in each of the room which has to be cleaned by this vacuum cleaner, and all that this vacuum cleaner has is a sensor saying that whether there is dirt in the room. If there is dirt, then just suck the dirt or move to a different room. That is the only sensor this vacuum cleaner would have. So it doesn't look at what has it done in the previous room. So this is how the architecture would be. Here we have the environment, where the environment would be interacted by sensors. In this case of vacuum cleaner, the sensors is dirt. This sensor would give you the information that whether there is dirt or not. It says yes, we have dirt, and based on that we have a condition rule saying that you need to do a suck operation now. Whenever it says there is no dirt, then this condition action rule would say that you have to move to your next room. So this is a simple architecture which is also quite useful in many use cases in real world. Most of the industry use cases implement such if else condition based agents, because most of them don't really need a historical information to do jobs. However, the major problem or the drawback of simple reflex is partial observability. What we mean by this is that we don't know whether the other state has already been cleaned or not. So what would happen in this scenario of a simple reflex is that this particular vacuum is in state A right now, and it receives this dirt and then takes an action of suck. After that, it has cleaned the room and then moves to this room and then looks at the dirt and then cleans it in this state. and after that it will move back to this room. It sees there is no dirt, and then it keeps repeating between the states A and B, and it never stops because it lacks what we call as a information about the environment. There is no internal state of the environment saying that all the states have been clean and then you can end the program. So that's why we call it as partially observable, and we are solving that with what we call as a model based agent. This model based agent is nothing but the information about how the world works, whether implemented in simple Boolean circuits or in complete scientific theories. So in simple facts, it can be as simple as keeping a state whether is clean. You can just simply say that you have two values in your data structure. It can be as simple as this, or it can be complicated based on the task that we are trying to handle. In the case of self-driving cars, you can have the model as whether it is raining, how much of brake has been applied from the car in your front, is there anyone moving on the road. So all this would actually consider under the model in the model based agent architecture. So how does this work? What we are trying to do in this particular scenario is we are trying to figure out what the world is like now based on three factors: the state that we are in, and what my actions are, and how does the world evolve. So if you remember from our previous definition of the task environment, a state and action cannot necessarily give you the end result of the environment. So if the environment is stochastic, you also need to know how the world would evolve so that you understand where are you in this world right now and how it is going to evolve. Once you are able to model this is called as model based agent. Using the sensors, we again use the condition rules to determine our actions. So this is the difference from the simple reflex agents. Now that we have the information of the world, we are much more intelligent in selecting our actions. Just recall from the task environment that the state alone would not help you. If you have the state and action, it would help you in few cases, but if you want to know exactly where you are in the world, then you should also understand how the world evolves. Like in the case of driving a car in the rainy conditions, you should know that it would be hard to brake, or you need to apply a lot more pressure on the brake so that you would stop where you want to. However, there are limitations of the model based agents. Like knowing the current state of the environment is not always enough. You also need to know where you want to go. Like in the same example of self-driving car, so if you have three possible actions to take, you have three possible directions, you need to pick one in order to reach your goal. So when you don't have a goal, then the model also cannot help you in selecting the right actions. So what would actually be an incremental improvement from the model based is to have the goal information, and we call that as a goal based agent, which combines the model information along with the goal information. So in this example, now along with what the world is like now, we will have what it will be like if I do action A. What does it mean is that if I take an action A, given the current state, will I reach my goal? Based on that, I will select an action. So if you are at a junction, if I take left, will that help me reach my goal? Or if I take right, will that help me reach my goal? Based on all that enumerations, we are now selecting an action, which would still be a condition based or if else based rule. However, now we added the information of where you want to reach. Again, the goal based agents alone cannot disambiguate actions. Still, you might have several actions to take. So let's say you are trying to move from point A to point B, and then you have two possible alternate paths. You can reach point C and then you can reach your destination, or you can go to point D and then go into point E and then reach your destination. So these two paths are still reaching your goal, but there should be a utility function which says what is the optimal path, which path should I prefer over other. This is modeled by a utility function. So this is nothing but it measures the performance of each action, thereby helping you select the right action. In this case, maybe we want to reach this in the fastest time, or in few other cases we want to reach it based on let's say other tasks that you want to finish at point D or point E. So in the traveling salesman problem, maybe you want to go through this path first compared to this path. So it depends on the problem, you have to select the right action. That is modeled by our utility function. So now we build something called as utility agents, which will combine the utility, the goal information, and the model based information. So in combination with the before architecture of goal based agents, we now add another variable saying that how happy I will be in such a state. This is modeled by our utility information. So if I take a route A versus route A dash, which one would give me the highest performance measure? This will be modeled by this utility function, and that would help me select the best actions. So far what we have seen is that while we are selecting these actions, we are still using something called as if else rules or the condition rules. However, these condition rules are very hard to scale depending on the problem. So what we have now is something called as a learning agent, which tries to learn the program in itself. That means we are trying to automate the if else rules if you have enough data. So the learning agents are actually learning based on how much ever data that you give it, and it tries to code the agent program automatically from the data. What advantages do we have over other methods? We initially operate in unknown environments. While we operate more and more, it actually becomes more competent than its initial knowledge. So this happens to be the preferred model in the state-of-the-art systems. This is what we are interested to solve in our future lectures as well. So let us try to understand this learning based agent in more detail. It has 4 components. We'll go into detail exactly what these components are, but to give a brief overview, these are learning element, performance element, critic, and problem generator. So performance element is nothing but, if you remember, this is our percepts to action function. Given percept, you try to identify what is your action. However, we have to modify this action based on our performance measure, our goal, and utility values. This is provided by our critic. It says how good is your action 1 versus action 2. It gives a value to each of those actions. Using these values, you improve this function using something called as a learning element. This helps you learn what should be the function f. What should be the function f that maps your percepts to actions. However, the problem generator is nothing but an exploration strategy to identify better actions by randomly choosing one every so in few steps. So this is the architecture of a learning based agent. We again have the environment, we have the sensors again. However, now we remove all those elements in between, and we have one performance element which determines what should be your actions based on your sensors. So this is a function which maps your inputs to outputs, However, when you're doing this prediction, you might often not have the best outputs at the current time t. So there will be a critic which actually gives you a score on how well you're performing. It gives you a score on how well are you performing. Based on this score, we have a learning element. The learning element uses this score to modify your performance element. So it keeps modifying the performance element, and that's how we get state-of-the-art performance compared to other architectures we have seen before. And we have a problem generator only to use as an exploration strategy. So in our next lesson, we'll be talking about the role of learning and expert systems. Thank you.